Antoine, if you would like to introduce us.
Okay, so welcome to this session of the LISA Symposium 14, and we will talk about data analysis. So we will have 3 speakers for the first part of the session. We'll start with Alvin Chua from Caltech, and he will talk about a needle in an opal field, reimagining Korean gravitational wave source. Alvin, can you share your slide?
All right, thanks, Antoine. Okay, let me.
Yes.
Okay. Right. So before I start, yeah, I just want to say, my connection is a bit dodgy, so I think I will, just to be safe, stop my video while I'm talking.
Okay.
And please let me know if the feed, if the sound drops out at any point in time.
Yes, I will let you know.
Yeah, thanks. So, okay, today I'd like to introduce some of my recent work, which is written up in this paper over here. So this idea is developed mainly in the context of memory signal analysis for now, but I will try and argue in this talk that it could also be useful in terms of how we should be thinking about coherent searches for LISA sources in general. Right, so first let's look at the basics. Now, coherent search is important in gravitational wave astronomy because it's needed to find sources with low instantaneous signal-to-noise ratio, and these would not be detectable with like excess power methods. So it essentially uses phase comparisons between the data stream X and some signal template H, and more specifically, it looks at this cross-correlation between X and H, which is weighted by a model for the detected noise. So this very familiar quantity here is a statistic of the data for any given H, but it can also be viewed as a function on the continuous space of templates for some given X. So there are, of course, many such statistics we can define, such as capital X here, which is the standard detection statistic for a single template. Now, the search for gravitational wave signals that are described by this model space then just simply involves finding a strong maxima in such functions and also to establish their statistical significance. So this procedure is known as detection. However, I should point out that mapping X correctly to the source parameters theta for any detected signal is also very important as well. And I will refer to this latter procedure as identification. And it is often overlooked because it can be trivial or unnecessary for many sources, but it still exists, at least implicitly. And for certain sources, such as MRIs, it's actually even the bulk of the problem. Okay, so coherent search for LISA is quite different from that in ground-based observing due to the distinctive nature of the LISA data stream. So the main difference I'll focus on here is that it's actually far more natural to use stochastic methods rather than a pre-computed grid of templates as done for LVK, compact binary coalescences. So this is partly because LISA binaries have more observable cycles in general, and thus they have a larger signal space. And also it's partly because there are stronger correlations between any given signal, as well as all the other actual or possible signals in the data. So these two factors actually combine with the high computational costs of certain source models in order to make a grid search a rather impractical option. So another important point is that we are constrained to use sampling rather than classical optimization algorithms. And this is because the coherent statistics that we use are not globally concave or even log concave on the model space. So in other words, the Monte Carlo sampling of statistic-based probability distributions is actually a more feasible way of exploring the signal space. And so in this way, search actually connects more naturally to inference in LISA signal analysis. And that's because the Bayesian likelihood itself, shown here, is also a coherent statistic. And in fact, on local scales, it has a very simple relation to X, as well as the optimal SNR rho. Okay, there are, however, some practical difficulties associated with coherent search. So in the case of LISA sources, we often find ourselves looking for a very small region or needle of probability in a large search area. So this is especially the case for MRIs and SOBHs. For galactic binaries, the problem statement, I think, is slightly different So there, we don't just want to find some needle, which is easy because there's so many to find, but the aim is actually to find as many as possible. Now, furthermore, these needles that we're trying to find, they are not on a hill, by which I mean there's no global gradient in the search function that leads to it. And this is the main reason why both sampling and optimization do not work very efficiently. So this gradient in the search function is either 0 in the case of X, the detection statistic, or for the log likelihood, it's driven by the optimal SNR of the unnormalized templates across the signal space. And that actually is even worse because it could actually take us away from the actual signal. So it gets worse because the search area is often the proverbial haystack or even a field of haystacks. And by this, I mean that there are many other regions in the model space that can look like signals as well to different extents. So these typically arise from two sources. One, there are the random correlations between detected noise and templates. So these actually cause low amplitude variations, but they do cause them everywhere in the model space. Second, correlations between the actual signal and other templates can also cause larger deterministic variations in the search surface as well. So this second point is particularly severe for MREs, and it has been characterized qualitatively in a recent paper that I wrote with Kurt Cutler. So that's referenced here. Okay, so all of these difficulties are essentially epitomized by MREs in particular. And that makes actually the identification of MRE signals quite intractable. So the first factor for this is that the scale of the region we need to find for MREs is at least 10 to the 20 times smaller than that of the full space. And second, the secondary maxima in the search surface can both be very prevalent as well as very pronounced. So in the study with Kurt, we found that a typical MRE signal can give rise to hundreds to even thousands of such maxima. So that's sort of depicted in this figure over here. And furthermore, the overlaps of all these non-local templates with the signal can be as high as 0.8. So essentially, they look like different sources with 80% of the actual source SNR. Now, one of the key insights from our study is that strong secondaries in the search surface, they have a very generic cause. So they require only the dominant frequency harmonic mode in both the signal and the template being nearly phase aligned for a good fraction of the observation duration. So I'll be coming back to this point later in this talk, so please remember it. Okay, so far we've only been looking at standard coherence statistics such as X or the likelihood L. Now, it's long been recognized that these can be difficult to search. So there are already various modified search functions in the literature that are actually geometrically different from either X or L. So these generally fall into two classes. The first of which is the principle of partial maximization or marginalization over some degrees of freedom in the signal. So examples of these sorts of approaches include semi-coherent statistics, where the data and the templates are partitioned into shorter time segments, and then the data template cross-correlation is maximized over time or phase shifts for each segment before they are being resummed over all segments. So that's this example on the left here. Now, F statistics are another way to do this, where some basis for the signal space is considered, and then the data template residual here is analytically minimized over the coefficients. So that's this example on the right. So all of these types of functions, they are essentially less informative comparisons between data and template. And so their general effect is to de-emphasize variations in the search function by broadening and coalescing peaks in the surface. However, something that's maybe a little unappreciated is that these partially maximized functions, they still retain variations due to both signal and noise correlations. And so the picture we have here is really still that of a haystack, but just with a bigger needle. Okay, there's another main way of modifying these search functions known as annealing, and this is often done as part of algorithms such as parallel tempering MCMC. So this de-emphasizes variations in the simplest way possible by just a rescaling of the function. So for example, the log likelihood here can be heated up by a temperature of T. So such approaches, they essentially smooth out the search function, in particular variations due to noise. But one thing to note is that they still actually retain strong secondaries relative to the primary peak. And so the picture here might be that of the same needle, but in a sparser haystack. So all of these approaches are perfectly sensible and they're quite well developed, but to me, none of them really seems to cut right to the chase. So here's a slightly heretical proposal. So I'm suggesting let's stop looking for needles in haystacks altogether. I think it's suboptimal. So the most optimal thing would be if we were able to put the needle on a hill, as I mentioned earlier. But if you think about it, there's really no way to do that. So I argue that the next best thing is to put it in an open field. And more precisely, I want to explore coherent search functions where all unwanted variations in the surface are exponentially suppressed. And at the same time, it's important that such a function preserves all wanted variations, which is to say we must still have strong peaks at the parameters of any actual signal. And while we're doing this, we might as well try to do even better by requiring that the function be analytically tractable, to have no tuning parameters, and to be fully informed by the template model. So if we can achieve this, then such a function essentially provides us with a one-stop solution to gravitational wave signal analysis, at least at the conceptual level. Okay, so to construct such a function, we basically need comparisons between data and template that are more discriminative than the standard cross-correlation, which is really just a single number. So a natural way to do this is to perform some sort of decomposition of the template into modes, which can then be compared against the data to provide extra information. So we can impose certain conditions on this decomposition here. And in words, really, the template model just has to be well represented by an orthogonal mode basis, but where the modes actually are required to have substantial power. That's this crucial first inequality. Now, for MREs, such a decomposition is available from the start because modeling and analysis approaches rely strongly on the decomposition into harmonics of the three fundamental frequencies in the signal. So here's a spectrogram for a typical MRE signal, and the tracks in red highlight the 4 harmonic modes that contribute nearly all of the power for this particular signal. So for SOBHs with generic eccentricity and precession, it's pretty much the same story, except that working with the frequency harmonics is a less common practice, and so these may need to be extracted from PN models. Now, for galactic binaries, there's no such complexity in frequency, but we might still construct a mode decomposition that satisfies the above conditions. For example, by partitioning the signal in the time domain. So it might be possible to use this new approach to help with the problem of source separation, but actually I haven't looked at this closely yet. And finally, for massive black holes, which generally have a lower eccentricity and precession than MREs and SOBHs, we could go the other way by doing a partition in the frequency domain. So, of course, for such signals, we already have decompositions into angular modes. But these higher modes, actually, they don't contain enough power to provide useful information for this approach. Okay, so the function I'm proposing has this general form. It combines information from 2 standard statistics, capital X, which we've already seen. That's the detection SNR, and plus a chi-squared-like statistic here, which is defined using the detection SNR of the individual modes. So as a concrete example, this function can then be calibrated for MREs through the definition of this the function beta, which is not a statistic of the data. So beta is built from information about the signal space at each parameter point. So more specifically, it encodes the optimal SNR row of each template, along with the fractional SNR of its dominant frequency harmonic, which I denote by alpha. So recall from earlier that the strongest secondaries for MRE signals are due to aligned dominant modes between the signal and the template. So the upshot of this calibration is that it reduces the typical height of such a secondary to the original level of noise variations, which is 1. And in the process, it also effectively eliminates actual noise variations by suppressing them to 0. So for other source types, it should also be possible to define beta in such a way as to be useful. But of course, we will need to come up with a concrete problem statement first. So for example, the aim might be to improve source separation for galactic binaries or to speed up searches for massive black holes. So that's work that's yet to be done. So here's a demonstration of the function for an example Emery signal space that's parameterized by 6 intrinsic source parameters. So there are a lot of curves in this plot, but let's focus first on the solid red curve, which is the function f for an observation duration of 6 months. And this is f evaluated along a straight line that's drawn between the signal parameters and a strong secondary in the 6D space. So the red curve, you can see has virtually no variations in it other than the main peak. And it's only marginally narrower at its baseline than the standard statistic x, which is the black curve. And this remains true even if no matter how you anneal x, and if you do so significantly, you get the gray dash curves. Now, the purple and blue curves here, they correspond to semi-coherent statistics with 6 and 12 time segments respectively. And you can see that they do broaden the primary peak as advertised, but they don't actually do anything about the small scale noise variations. So you might say that the narrow peak in the red curve is going to be harder to find than that in the purple or the blue curve when you're doing a full dimensional search. So if that's true, one can still use less informative comparisons in combination with exponential suppression in order to broaden the peak as well. So for example, if you just do a simple truncation of the observation duration to 3 months, that gives the dashed red curve in this plot, which clearly has a broader peak. But to be honest, I don't even think the narrow red peak will be harder to find because I'm convinced that the broader peak in these semi-coherent functions is actually not going to be enough to offset the greater difficulty with which the chain actually traverses the rest of the space. And of course, the ease of traversability for any search function is directly related to how smooth it is. So this may sound a bit obvious in hindsight, but it's also straightforward to show using a metropolis Hastings chain that I direct along the line from the secondary to the signal. So this figure here essentially shows 1,000 realizations of such a chain for 4 of the functions in the previous plot. The vertical axis here is the location of the walker. And the solid lines, basically, they indicate the median location of these 1,000 chains over time, which is the horizontal axis. So the chains that are traversing the function f are indicated in red, and they are the fastest on average because f is simply the smoothest in the probability tails. Okay, so in summary, in this talk, I have claimed that all of the existing coherent statistics that are used in gravitational wave research, they are actually suboptimal in terms of efficiency. And this is solely due to uncontrolled variations in the search surface. So to address this, I propose a new class of coherent statistic that exponentially suppresses such variations to a constant baseline over the model space, while it also retains strong peaks at the location of actual signals. I also then demonstrate that these type of function can be calibrated for Emerys in a natural and well-defined way. Okay, that's all. Thank you.
Thank you, Alvin. Thank you very much for the talk. Any question for Alvin? You can raise your hand or ask question in the chat. Wait. I don't see any question. I have a question. How do you calibrate beta, this particular function that you have in because it seems important. It seems to be the key point of your method, this calibration of the.
That is correct. It is the key point when applying this.
And how did you come with this function that?
Yeah. So yeah, it is actually the important thing. You're absolutely right. So for Emerys, basically, it is informed by the fact that the strongest secondaries, as I mentioned, they are caused by essentially the template and the signal having dominant modes that line up pretty much for the whole duration of the signal. So from that knowledge, you can actually say that you can, for any given template in the space, you can calculate roughly what's going to be the overlap with another template that matches just the dominant mode.
Mm-hmm.
So using that information, you can then essentially say, I want to reduce the height of such a secondary to 1. And that's done throughout the space. So that's essentially how the calibration is done for MREs. Yeah.
Okay. Tyson, you have a question?
Yeah, so preface that I warned I had to be multitasking this morning, so I might have missed this. But your replacement of the standard statistic with this new function, is that purely for the sake of sampling efficiency, or does this, effectively like replace the likelihood as part of the thing that you are sampling over?
Right. So no, it's not a replacement for the likelihood, because the likelihood is pretty well defined. So what it is I think what you said at the start, it is mainly just driven by the need for sampling efficiency. And in particular for MREs, which is the first thing this is applied to, sampling efficiency takes a very huge hit because of the presence of strong secondaries.
Mm-hmm.
And right. So at the end of the day, the samples that you get are the equivalent to samples that you would get from sampling the old-fashioned way, just much more quickly. So you don't have to worry about, implicitly reweighting the prior, basically, because you've changed the statistic.
Yeah, that's sort of correct. Actually, there is a sort of a close relation between the function and also the log likelihood as well. So I think in this paper, I actually try to argue that if you just sample from the function, you do end up with a final set of samples from that distribution. And I argue that it's generally always slightly broader than the bulk of the posterior itself. Mm-hmm. And if that's the case, then well, it's broader, but it's not too much broader as well. So it's pretty well localized. So if that's the case, then it could work pretty well for prior localization, or even if you want to use the samples directly, you could just assign importance weights to them. So that's the idea. But they're not exactly posterior samples, if that's what you're saying.
Yep.
Thank you. If there are no other questions, thank you, Alvin, again. And
thank you.
Thank you for this very nice talk, an interesting method. We need to do that in practice. And now we will switch to Alexandre Toubiana from AI. We'll talk about the detectability and parameter estimation for Gaussian wave catalog 3 event with laser.
Yes. Hi,
so, Alexandre.
Yeah.
Okay.
Can you see
we can see your slide. We see the bar with 30 slides. That's a bit scary, but
no, don't worry. It's a lot of backup slides.
Okay.
Okay.
Okay, you can start.
And if I change slides, you'll see, right? Okay. So hi everyone. I'm very happy to be here today to talk about this work that I have carried with Stas Babak, Siva Massa, and Sergei Osokin on the detectability and parameter estimation of events in GWTC3 with LISA. So the interest for the detection of stellar mass black hole binaries with LISA has grown a lot after the detection of the first gravitational wave event, because at that time it was suggested that this event could have been detected by LISA, leading to multi-band observations with LISA and ground-based detectors. So since then, there have been many studies on these multi-band events, and it has been shown that they could allow to measure low-frequency modifications to the gravitational signal, which could be due to modified gravity or astrophysical effects. Another interest of detecting the systems with LISA is that by the time they are in the LISA band, they could still have large eccentricity, and this eccentricity information could be used to distinguish between different formation scenarios. However, the population that we expect to of the systems that we expect to detect with LISA, it's largely unknown. So we could use on one side astrophysical simulations to predict the population of events. However, well, so those rely on a set of assumptions, and also they tend to give the results tend to disagree. There is no consensus yet on what to expect. We could also use the results from the LIGO-Virgo collaboration population in France. So use some of the models they have fitted against data for the population of star mass black hole binaries, but this is again somehow model dependent. So here instead, we use a more data-driven approach. So the idea is to use the events that directly use the events that LIGO and Virgo have detected so far, so that have been released in this gravitational wave catalog, and to see which of these events could have been detected by LISA and how much would the parameter estimation for these events improve by using LISA. Okay, so what LIGO and Virgo give us is, so for each event, we have samples for the parameters of the system. So for each event, we use the samples for the masses, the spins, taking the projection on the orbital angular momentum axis, the inclination, and the distance. And moreover, we assume that the binary, so here we will just focus on the circular binary case. However, we randomize for each of these samples the sky location, the polarization, and phase. Now, so the last parameter to fix is the time to coalescence. So in this study 2 years ago, we had shown that actually this is a very important parameter so depending on at which stage you observe stellar mass black hole binaries with LISA, the result for the parameter estimation in particular can vary a lot. The best being to observe the system closer to merger when it starts chirping. So for this reason, we consider here three different possibilities, so three combinations of time to coalescence and observation time. And finally, so after having defined mock LISA systems with this procedure, we compute the signal to noise ratio using the science requirement PSD, and also the current best estimate, which in the frequency range where these sources evolve is lower, it's better by a factor square root of 1.5 than the SIRGV1. Then we consider two different thresholds for the sources. So one for direct observation with LISA. So the idea is that we would observe them before ground-based detectors. And for this, we take a SNR threshold of 8. And we consider another threshold for archival searches. So the idea being that after ground-based detectors would have detected the source or have a better idea of the parameters, we can decrease the size of the parameter space to look for the source, and we can use a lower SNR threshold, which here we take to be 5. I will not enter into the details right now. You can ask me later, but we do give in the paper somewhat justification for these thresholds. Then, for each of the events in the catalog, we compute the probability of direct detection and of archival detection by computing the fraction of samples that have SNR above 8 and 5. Okay, so to show now the results. So if we use the current best estimate PSD, so here I'm showing the distribution of signal to noise ratios for all the systems in GWTC3. And in color, I'm highlighting the systems that for each of the time to coalescence observation time combination have a probability of being detected for archival search above 10%. And you can see that as expected, if you observe the systems closer to merger and for longer, the SNR increases, and so does the detection probability. So being now a bit more quantitative, I'm showing this detection probability for a few systems. So first, if we look at the first gravitational wave event, you can see that it's very likely, mean, almost essentially guarantee that we would have detected it through archival searches, but not so certain that we'd be able to detect it directly with LISA, in particular if we were to observe it far from merger. Now, this other system here is the only one that has a higher than 10% probability of being directly detected, and this only in this most optimistic scenario. And then you can ask the question of probability of detecting at least one system in the whole catalog released by LIGO Virgo. And so you can see that the values that I'm showing here are actually very similar to the one in the first column. This is because this event is really driving these values. So instead, we can ask the question of detecting at least one system other than GW19 or 914. And an important remark that actually in each of the columns, I am assuming here that all the events are detected exactly at the same time before coalescence, that they have the same time before the coalescence and observed for the same period, which is certainly won't be the case. So actually you could see the leftmost column as the pessimistic case and the rightmost as an optimistic case, and take them as lower and higher values. So you can see that it is reasonably likely that we would detect at least one other system than the first gravitational event through archival searches, but it's much less guaranteed that we detect any other system directly with LISA, even in the most optimistic configurations. Okay, so now addressing the question of parameter estimation for some of these systems, we focus in on the most optimistic case, and we consider one system that would be directly detectable with LISA, and another one that would be detectable only through archival searches. Moreover, so we mimic a multi-band detection by using a Gaussian prior in the Bayesian analysis, and the covariance for this Gaussian prior is computed using the samples released by LIGO Virgo for masses, spins, distance, and inclination. And in addition to that, we fix the coalescence time of the binary, because this is a parameter that is usually very well measured by ground-based detectors. We also mimic a LISA with Einstein telescope scenario by just rescaling this covariance matrix by the relative gain in signal-to-noise ratio from LIGO Virgo to Einstein telescope. And an important point is that this is a very conservative assumption, because we're neglecting the fact that ET would actually observe the system for much longer due to its improved sensitivity at lower frequencies. And this would have in particular a big impact on the measurement of chirp mass. But this still should give us an idea on what LISA could help improving in the parameter estimation. So if we first look at this one system, which is directly detectable with LISA, you can see that actually LISA can, so here I'm showing, the 90% confidence interval in the chirp mass symmetric mass ratio plan. So you can see that LISA could perform actually much better than current LIGO Virgo, and that it can measure the chirp mass also better than with this rescaled Einstein telescope that we're considering. However, it performs much worse for the mass ratio. And so combining these, when you look at the estimation of the individual masses, adding LISA, in fact, gives only little improvement, as you can see on the right panel, comparing the orange and the purple curves. We have a very similar picture here for the spin. So LISA can measure quite accurately one spin combination, so the effective spin, but not so well the corresponding anti-symmetric combination. And when you translate into individual spins, adding LISA, in fact, has not big impact on the measurement of individual spins compared to using each alone. Now, if we focus on this other system, which is detectable only for archival search, so it has Lisa SNR around 5. So there is no, here we don't have a Lisa only case, but we can see that adding Lisa to each actually, so again, improves a lot the measurement of the chirp mass and also a bit for the mass ratio. And in this particular case, once you combine this, and you see for the individual masses that Lisa can help improve a bit the measurement of the masses. And finally, so for the spins, it's again a similar picture. It can help improve a bit the measurement of the effective spin, not so much of the other spin combination. And so it has almost no impact when you look at individual spins. But it's important to stress again that this is a very low SNR system in Lisa, so around 5. And we see here, at least for the masses, that it still has some impact on the measurement of the parameters. So just to mention a few other parameters, so the sky localization, and just to remind you that here I'm using Lisa only, I'm not using any information coming from ground-based detectors. We get that for the system that is directly detectable, it's measured within 1 square degree and within 2 square degree for the other system due to its much lower SNR. Finally, for the distance, so the distance measurement is essentially driven by the prior that this ET prior that we are using. So when we use it, we can measure the distance within 5%. And when we don't use that prior, so we use the LIGO Vivo prior or no prior at all, we can see that the measurement is much worse. Okay. So as a conclusion, so here I've shown that the detection of GW19 914 with Lisa would have been almost guaranteed, at least through archival searches. However, if we want to look at the rest of GWTC3, it's rather unlikely that we would have detected any other system directly with Lisa. And perhaps, so we could have, so it's more likely, although not certain, that we would have had some iCavo detection. Finally, so also I have shown here that even for rather low SNR systems, we find that Lisa would improve the measurement of chirp mass and effective spin, but usually when you translate that into individual masses and spins, Lisa has smaller effect. And so just to say now, for I think some important improvements to our work would be to proper multiband, not only using these priors as we did here, and also very important to include eccentricity. And so there have been some important steps in this direction very recently. So yeah, I hope I have convinced you that there is still some interest to look at stellar mass black holes with Lisa. And yeah, please don't hesitate to ask questions.
Thank you very much, Alexandre. Question, Tyson?
Yeah, I have a lot of questions. So
okay,
the one I'll ask first is, so by reducing the detection threshold, what you're effectively saying is you have fewer degrees of freedom in the search. Which parameters are you not searching over?
So, okay, sorry, maybe this I was not clear enough. We are not performing a search here at all. So, okay, we are not really performing a search. We start always from the true signal. And when I reduce the SNR threshold, I mean, what I mean considering is more the fact that that I can decrease the size of the parameter space rather than decreasing the dimensionality of the parameter space. But one interesting thing that we found is, so here I'm showing, so the chains that for one particular system, which had SNR in Lisa, as you can see, of 4.5. So we started our chain from the true point, but you can see that at some point, the chain loses the signal and then finds it again. and then loses it again. So you can see here in the chirp mass, or also when you look at the log likelihood values, you can see that when you're exploring these much broader regions, which correspond to the prior that we're using, it corresponds to much lower likelihood values. So although originally we're not performing really a search because we're starting from the true point, in the end, what we find is that if the system has a Lisa SNR below 5, even in this case, you could lose the signal.
Okay, so then I guess that dovetails to my follow-up question. So what are you doing about the time to coalescence here? And the reason I ask is because, like you said, eccentricity is really the strongest lever arm. And in the LIGO Virgo Kagra band, there's not all that much eccentricity to measure. I don't have much intuition here, but I imagine small fluctuations within the, effectively zero measured eccentricity at merger make for large fluctuations in when the signal leaves the Lisa band, and certainly completely washes out things like the phase of the signal while it's in the Lisa band. So how constrained are you on just the effective time of coalescence when you're doing the analysis in the Lisa band, and how much uncertainty do you think there is in that parameter once you consider very small residual eccentricity?
So as I said, here we are taking only circular binaries. So here we don't have eccentricity, and unfortunately I never so far have not considered eccentricity when doing parameter estimation for these sources. So what I can say is that for the time to coalescence, usually if I don't put any additional prior with Lisa, it's measured within 30 seconds, 1 minute. I think I cannot say much more than that, unfortunately, because as I said, I have not used really eccentric waveforms. But I think this is very important steps now to be done. And as I highlighted at the end, I think we're starting to be able to do it now.
Yeah, so I mean, you mentioned it as future work. I'm very excited to see that future work.
Thank you.
Yeah, me too. I had a question about when do you think that already are we for considering eccentricity in this kind of study?
So there has been a first full parameter estimation with eccentricity, so by Antoine Clental.
Yes.
So I think so. I don't know if Antoine is here, but I think one of the major issues right now is the computation is very slow because of the waveform, but they managed to do a full parameter estimation. So I think now we should be able to start doing this.
Okay. Thank you. Any other question for Alexandre? Yes, Changju, please.
Okay. Can you hear me?
Yes.
Yeah.
Okay. I have a question. Have you considered the noise when you try to search the signal? Will that, or if so, will that affect your parameter estimation result?
Right, good question. So indeed, I did not mention, but here we are working in the zero noise approximation. And yes, so definitely also, I mean, if you just what this plot is telling us is that once we add noise for these lower sources SNR, so you could expect that this would drive you away from the real signal.
Yes.
So, and then if you increase the parameter, so yeah, the main effect of noise should just be to move you within the 90% confidence interval. So that, yeah, I think so it's a very good question, in particular for these lower standard sources. So no, we did not consider it, but this is also something actually that we were discussing recently with Sylvain that we should certainly account for in this. low SNR. So for as you go higher in SNR, I think this is less of a problem. But yeah.
Okay, yes, because most of the stellar mass binary black hole signal, their SNR will quite low in the space-based band, right? So when sometimes consider the noise, the SNR will be too low, and it's take quite a long time to let the MCMC or their teams to conserve to the true signal. So I also think it's a really good problem to consider.
Yeah, I agree. So I think that's one of the things also we want to look next is now doing the full PE adding noise. Because indeed, I mean, this is, so what you're saying is in fact exactly what these plots are showing is that most of the systems will have really rather low SNR in LISA.
Yes.
At least based on what LIGO Virgo have seen so far.
Okay.
Okay.
Thank you.
Thank you.
Thank
Any
you.
more questions for Alexandre? If not, thank you, Alexandre, again for this very nice talk.
Thank you.
And now we will listen to Connor Weaving from University of Portsmouth about the search of massive black hole binary with PICBC. Connor, are you ready? And can you share your slide?
Hi, yeah, I'm just setting up now. How's that? Can you see everything and hear me okay?
Yes, it works.
Good stuff. Okay. So hello, everyone. My name's Connor Weaving. I'm a second year PhD student at the University of Portsmouth. And my project so far has been on the search for massive black hole binaries using the LDC dataset. And we are currently developing these data analysis tools to be implemented within PyCBC, so an open source bit of software which everybody can use. Yeah, just a note on that, obviously we are developing all of these tools within PyCBC, but we are also looking to expand into other open source bits of software as well, such as Bilby. But yeah, currently it should only be available through PyCBC, but yeah, hopefully we'll move on to Bilby as soon as everything's settled with PyCBC. So let's jump straight into it. Yeah, as mentioned, we are building this data analysis pipeline to detect massive black hole binaries, and we are using the LISA Data Challenges dataset in order to help us do that. And we're using these Sangria datasets. We're using the massive black hole binary dataset. And this dataset in particular contains, well, this is the blind dataset that we're using to actually build the pipeline, and we've got 15 signals here which are hidden in mock LISA data. Yeah, so this is what we've been using to train and build all of our tools. So what constitutes a pipeline? What is the purpose of what different sections are there to these pipelines? And they're normally split into two different things. So you've got the search part of a pipeline, which is basically where are the signals within the data. And we use our basic techniques such as match filtering, and we are looking into template bank searches in this particular case, which I'll tell you a bit more about at the end of the presentation. And then you've got the second part, which is the inference, i.e. what parameters, values are there of the gravitational wave signal that we've found. So yeah, so the first part, we'll start with the search. Apologies, for some reason the slide seems to be a bit, seems to have changed slightly. I'm not sure why, but anyway, the quality on the left is a bit rubbish, but anyway. So yeah, we've got our standard match filter. So the animation on the left demonstrates this. The blue line is just gravitational wave strain data. The yellow line is a gravitational wave template. And the red line is the SNR time series. So using this equation on the left-hand side here, which this is the SNR, you should be able to find a peak within the SNR when given a template and some data, and that will tell you roughly where this peak is within the data that you're given. So this is all implemented and done within PyCVC, which is great. So this is just one example of just one match filter search, and this is just using one template, I should say, over the entire year's worth of data that the LDC have for the Sangria dataset. So as you can see, there are multiple peaks across the entire year. So I think there's 14 peaks here which you can distinguish. We know there's 15 in here. So yeah, it's pretty good going just with one template that you can pick out all of these different signals all at once. Previously, we were using code which we wouldn't be able to implement into PyCVC because it wasn't open source. However, a big shout out to Michael Katz, who released his fast waveform, well, fast TDI generation code, BBHX, and that's what we are using as our waveform generator within PyCVC for all of this stuff, right? So yeah, the template bank generation is done with this waveform generator and the inference as well. When we're generating new templates, it's all using his waveform generator. Again, apologies, for some reason my slides are going a bit strange here. There is supposed to be more on this slide, but anyway, yeah, moving on to the second part of the pipeline, you then have the inference, right? So we've already seen that we can find all of the signals within the data, but when we find them, we need to then infer the properties of that signal, and that's using Bayes' theorem here, right? There should be a picture here, but anyway, we'll just ignore that. Yeah, I'll skip on to the next slide, actually, because there's a nice corner plot here. So originally, we started using the marginalized phase model, and only one TDI stream for simplicity, and we'll build complexity as we go. So here's one of the very first plots that we were able to plot using PyCVC and the waveform generator. So it's very simple, and as you can see, the masses are recovered quite well, but the time of coalescence is off and the distance is off. But after fixing bugs and adding more complexity, we managed to solve the time of coalescence problem. And as you can see, I've added spins into this posterior graph as well. But there's still some slight problems with this, mainly due to the amount of time that the marginalized phase model takes to infer these properties. So we had to find a different solution here, and we looked to relative binning, which is a way of ensuring that you don't have to compute such a complicated integral more than you need to. So, for example, if you have a very high likelihood template, you can use that as like a reference template, right? And relative binning uses what's called a heterodyning. So if this is your signal at the top, this can be deconstructed into a higher frequency component and a lower frequency component. And the idea here is that if you have a reference template, a very high likelihood, so you're very close to the peak, very close to the true values, this integral can be computed and stored. And because it's very fastly varying, obviously this is quite a heavy computational cost, but if it only needs to be computed once with the reference parameters, then that's great because you can store that in memory and you don't need to keep redoing this integral all the time. So that means when we're searching near the peak with a new template, this slowly varying template will be the one that we can use. So when we're searching around the peak, we actually only need to compute this very slowly varying template, right? Which makes it a lot faster, which is, yeah, been working very well as well. So this is kind of the pinnacle of where we're at the moment with implementation of the inference. So we have relative binning working. We can use all of the TDI streams produced by Michael's code, by Michael's waveform generator. And this is a search over all parameters apart from some of the sky location parameters, right? And as you can see, it's agreeing quite well and it's looking quite good. Yeah, so with the inference stuff, there are still some slight problems like well-known sky parameter issues. but overall, it's looking sensible, and I think we're coming to a place where we can, start implementing this properly into PyCPC and making it a bit more public for people to use. Yeah, so as mentioned, there are still some issues with the sky localization because this dataset is produced using only 2-2 mode waveforms. You get these multimodal sky positions, which you can solve in different ways, but we know that it's going to be a bit of an issue for sky localization, which is fine. Yeah, we're currently still trying to make tweaks to that to make sure that we get sensible results back. But the main thing is going from the search stage to the inference stage, because finding the signals is one thing, but in order to get the reference parameters that you need for relative binning, there's quite a big gap, right? So, you'll generate a template bank, and that template will probably be way off the true value needed, or the reference value needed, rather, to then do inference. So there's a couple of ideas that we're searching and investigating there to see how we get from those initial search stage to the inference stage. Yeah, so in summary, the basic tools are almost there. There's still a few little tweaks that we need to do to make sure that it's all smooth. There's still some issues with the sky localization. However, we have done some searches with Sangria, and they seem to be working quite well. So yeah, we're hoping by the end of the year, we will have this all packaged up nicely and available for everybody to start playing around and use. So yeah, thank you for your time. I'm happy to take questions.
Thank you very much, Connor. Question from Tyson.
Yep. So the lore has always been that the parameter space is too large and the targets are too small, and you would need so many templates in the pre-computed bank before doing the search that it quickly becomes unfeasible. And that's sort of what drove people towards stochastic sampling algorithms, decades ago, back in the MLDC days. So are you searching over a more restricted parameter space, or has there been some change of the lore?
No, so yeah, currently we're only really generating, because if I go back to this search, actually, hang on. Yeah, so given that's just one template, we thought that we don't need really such a dramatically big template bank to find the pings, well, to find all of the signals within the data, right? So at the moment, we're just testing with a template bank of 100. We're allowing it to randomly generate those templates between quite a large range, the full range, right, of what we expect. And we are finding all of the peaks within the data with just just 100 templates. And I suppose the idea that we had was that if we can get all of the time to coalescence with some rough, parameters to start with, then we can begin to sort of optimize and find those peaks. And we've had a couple of ideas about, like particle swarm optimizers and stuff like that to get up to these reference parameters needed for the inference. So I know the stochastic route has obviously been used before. We just wanted to try it out and see if it could work. So yeah, does that answer your question?
Yep. And then a follow-up. So when you do this on the Sangria data, are you just powering through the galactic foreground, or are you using data where the galaxy has been pre-subtracted because you are using the training data and know what the right answer is, or what do you do?
Yeah, so we are generating the A and E TDI streams. We're then generating the PSD of the entire year of both of those data, and then giving that along with the match filter. So that's the way that we're doing that. Yeah.
Okay, so it has the galactic foreground in it.
Yes. Yeah.
Okay. So you are ignoring the effect of the galactic foreground and trying to search like that. Okay.
Yes, exactly that. Yeah.
Yan Dong.
Okay, thank you. Can you explain more about the problem of sky localization? I didn't hear understand it clearly. Thank you.
Yeah, sure. So the problem, as I understand it, is that the injected gravitational wave signals within this data set are of the 2-2 mode only. And there are well-known multimodal effects with just using a 2-2 mode waveform when you're searching for it. So this ceases to be a problem when you're using waveforms that have more than just the 2-2 mode. However, because this is just a 2-2 mode data set, we are searching with just the 2-2 mode, and therefore you have these multimodal sky positions. That you can break some of those degeneracies by searching within the LISA frame, but there are still these multimodal effects. Does that make any sense? And would anybody like to add something on top of that who knows more than me?
Okay, thank you.
I would like to add the column.
Yes, I was expecting that.
Yeah, I saw Staz's hand go up and thought, yeah, okay.
It depends on the duration of the signal. If you don't see much of the spiral, what you see on only merger, and what you measure is the time of when it hits, gravitational wave hits different spacecrafts, and therefore it gives a strong degeneracy in if you see only merger, and a point which is symmetric with respect to LISA plane, just above and below it. And that is strong degeneracy, which is unfortunately will exist if a massive black hole signal is short. And one of the advice is here to go into the LISA frame instead of solar system barycenter. And then this maxima, this bimodality is quite symmetric, and you can manually explore these two parts.
Christian, do you have a question?
Yeah, so that was a very nice talk, thanks. I was just going to ask about whether you've been able to investigate what kind of sensitivity penalty you have for the 100 template approach that you just described, because presumably if there's a signal in data and you do not use the right template, then you're going to be less sensitive. And obviously for many MBHBs, that's not going to matter too much because the SNRs are so large that you're going to see them anyway. But the fainter ones are higher redshifts, which are quite valuable as well. You might not see these with this method, and indeed you would only really be able to pick these out either with a very fine template bank or with stochastic methods. So I'm wondering if you've been able to assess what kinds of sensitivity penalty you experience with this approach.
Yeah, it's a good question. Currently, no. We're still tweaking and messing around with the template bank stuff. Yeah, we did try to do like a match-based template bank generation with 100 templates, and we did get very similar answers. So at the moment, the idea that we have is just right. Can we just find the peaks? Can we just find something, and then from there, you've got some kind of rough time of coalescence, and then you can do. You can pass it on to your optimizer to try and find a peak. But yeah, that's a good question. No, we haven't really thought about that just yet, because we're still, we're kind of just wrapping up the code that does this for you, right? So no, that's probably something that we'll have to look into. Well, sorry, that's something that we'll definitely have to look into. Yes. Yeah, thank you for that.
Okay, yeah, thanks. It's just because I was wondering how if the sensitivity to the parameter space position that your templates are in, if that is not strongly correlated with the true parameters of the signals, but the signal SNRs are very high, then they will have narrow posteriors, and so your the positions in parameter space where your template bank is returning high likelihood might be quite far away from the truth, which is maybe a little bit problematic. There are a lot of the reason I ask this is there are a lot of methods for identifying very bright transients like this in data, but I was wondering how effective necessarily this was compared to others. But yeah, thanks.
Yeah, thank you. If there are no more questions, thank you again for the talk. And I think we have a break. We have 5 minutes over the time. So Alastair, what are we doing? We are convening in 10 minutes or in 15 minutes?
I don't mind. I leave it to your discretion, or people can Well, let's just say that we'll give people the
time
full
to take-
the full
Okay.
15 minutes. So we'll come back at 20
Yes,
past.
yes, 20. That's okay. Okay. See you in 15 minutes. Okay. Can you hear me? Okay. So let's restart this this session about data analysis. So our next speaker is Robert Rosati from NASA Marshall Space Flight Center, and Robert will talk about the detecting primordial stochastic gravitational background with LISA using Bayesian inference. Robert, can you share your slide, and you can start when you want.
Okay, can everyone see that?
Yes, we can see the slide. Yes, perfect.
Okay, excellent. So I'll go ahead and get started. Yeah, so I'm Robbie Rosati. I'm a postdoc at NASA Marshall working with Tyson. And I'm going to talk to you guys today about our work in progress for detecting stochastic backgrounds and the LISA data. The goal is eventually to integrate this into the global fit pipeline. So as I'm sure this audience knows, there will be quite a lot of sources in the LISA band. We've heard a lot about discrete sources that emerge in a finite amount of time. But there also might be stochastic sources, which are too indistinct in time or frequency to resolve. And we expect there to be a few astrophysical sources, the unresolved galactic binary foreground, potentially an extragalactic background from LIGO Virgo bands and spiraling black holes. And on top of that, we might as well have some primordial sources, which is mostly what I'm going to be focusing on. So if you've heard some of the cosmology talks during the symposium, you've heard some about the primordial sources we might have in LISA. The dynamics of inflation, depending on how it happened and how many fields were involved, can potentially create stochastic backgrounds. And yeah, my background's actually in inflationary cosmology, so I'll talk a little bit about those signals in detail. The end of inflation, reheating, can also create stochastic backgrounds, depending on how exactly it happens. As well, we know there were at least 2 phase transitions in the standard model, although in the vanilla standard model, neither of them actually create gravitational waves. But there's good hope that a modification to the standard model could make this ultra-weak phase transition create gravitational waves by making it a first-order phase transition. And if that occurs, then just from luck of the energies involved, it'll be directly in the LISA band. So there's quite a wide variety of these signals, and I'll talk more about them later. But the basic detection strategy we have is you really need to use all 3 channels of LISA in order to distinguish signal and noise by their correlations. So when you form the AET TDI combinations, this T channel at least lets you, at least at low frequency, lets you probe the instrument without signal, which you really need to do in order to distinguish them. And there's some caveats about the T channel. I think there's a talk about that tomorrow, which I look forward to checking out. And just using the AE and T channel, you should be able to find all the excess power that's not instrument noise, if your noise model is correct. But that doesn't really tell you anything about the physics involved. It doesn't tell you if that stochastic background is from a galactic source, extragalactic, or primordial. If the instrument has non-stationary noise, you have to take that into account as well. And if there are discrete merging sources that are finite in time, you need to make sure that those aren't affecting you as well. So the procedure we have for now is to use stochastic templates. So these are just essentially frequency domain templates for a bunch of primordial sources. Here's a handful of them plotted on the right. And the great benefit of using templates like this is when you have overlapping signals, you can decompose them. If the signal is there, you get automatic parameter inference. If it's not there, you get an automatic exclusion plots. And we can do all this in a Bayesian way, so we can integrate it into the global fit pipeline under development, and that will automatically take care of the discrete time signals. So keep in mind this green curve here. This is like a model of an electroweak phase transition. So I'll come back to that. So we've implemented this pipeline and have done some like preliminary signal injections and recoveries. So the procedure for now has just been to do everything in the Fourier domain. So this green here is the T channel, and orange and blue are the E channels. And so we just generate the data using the standard noise curves and take the signal, multiply it by the standard instrument response, and use that to create the expected PST in each channel, which would be this red curve here, which has a couple of injections already. And then from this red curve, we synthesize Fourier domain data with the correct PST and a random phase, just by taking this X and Y to be unit normal random numbers. The likelihood in Fourier domain under the assumption of the equal arm instrument can just be written this way, where you compare the PSD of the Fourier domain data directly to this theoretical covariance. That was the red curve there in the last slide. Okay, so let's try out. So we one of the first things we tried was pretty similar to this Radler data challenge, which has a simulation of the extragalactic background in it. So we're generating our own data in this case, and it's similar to that. And the amplitude of the background is quite high, which I think current expectations are that it's a bit lower than this. And it's quite loud in the Lisa band. We're able to recover it in only a few days of data, assuming there are no other sources, right? But the error bar is quite large until unless you use a few years, you can recover it a little bit more accurately. And the sampling here was all done with Dynasty through Bilby, and the likelihood and all the templates are written in C. So I talked a lot about primordial signals. So let's take a look at one of them. So the that green curve I showed you a few slides ago, the electroweak phase transition, or one model of it, can be written this way, which is kind of a two-part broken power law, expected to be fairly low amplitude compared to the previous signal. And we can inject and recover that. For now, I put in a large amplitude to only use a short amount of time and data. I think this is 2 months of data. We can recover that well. And I think Mark Hidmarsh is giving a talk concurrent with mine actually in one of the other parallel sessions about this type of signal. Okay, so at least in principle, we can inject and recover these stochastic backgrounds, but that really ignores, all the other things going on in the Lisa band, of which there are quite a lot. And assumes we have perfect knowledge of the noise model and everything like that. So one idea we had is we could definitely take into account the galactic binaries if we could model them as a stochastic signal and then chunk that signal in time. So say, independently fit for at least this amplitude, this A1 here, every single month of the Lisa data. And in principle, the time variation should just depend on the antenna pattern of Lisa relative to the galaxy. And if you fit these parameters at 6 months of the galactic background, these are what you get. So we took these to be like a typical injection and took priors, wide priors around them. And when you're chunking the data in time like this, you can just assume the likelihood is a product of each chunk's likelihood. So here's an injection and recovery of galactic background with two different likelihoods and 90 days of data chunked into two groups. And so the first chunk, the amplitude, the A1 was 10 to the minus 10. The second chunk, it was 10 to the minus 11. So, and all the other parameters were assumed to be constant between the two chunks. So in that way, we're able to take into account the varying galactic foregrounds while having some constant parameters for the instrument noise or other parameters of the signal. And since we're interested in primordial signals, I thought it'd be a good idea to inject one on top of this galactic foreground. So this signal is the stochastic background you'd expect from a spike in the primordial power spectrum. So if you tried to form primordial black holes of just a fixed mass or have like a very sharp feature in an inflationary model, this is the sort of signal you'd expect. It would be much smoother from a realistic model. But this is a sort of a model independent rough shape of this type of physics. So we injected one of those and tried to recover it. Here we took 4 months of data, and the galactic foreground has a different amplitude in each month. And 2 of the months overlap here in the middle. That's why you only see the purple, you don't see the green. But we're able to recover that quite well. And take into account the varying galactic foregrounds. Okay, so that's more or less our work so far. And so, I'm working on building up the stochastic signal template library. And if anyone has a stochastic template I should take a look at, please, let me know. Happy to. We need to integrate this into the global fit pipeline, so that would involve changing the noise model instead of just kind of the analytic 2-parameter noise model. We need to work with the global fits noise model. So this is a little more complicated, non-parametric. And ideally make this kind of a transdimensional sampler, so we can automatically figure out how many signals are present in the data and what their characteristics are. The cosmology working group has this SGW binner, which is kind of a model independent excess power sort of reconstruction of the stochastic background, which is kind of the a model agnostic approach. And also there are more sophisticated models of the confusion noise and isotropic properties. This one from Neil Cornish and his postdoc, Max Digman, looks very interesting. So, okay, so that's it. Anybody have questions?
Thank you very much, Robert. Ruby. Any question for Ruby? Quentin, please.
Yes, very interesting talk. I had a question, well, a bit technical, but when you're analyzing years or 6 months worth of data, you have a lot of frequency bins to consider. And so are you applying some kind of averaging, binning, or smoothing like the SGW binner to make your analysis quicker?
No, I'm not for now, which is why I have the likelihood in C to make it a little faster. But yeah, for now, I'm just taking the raw Fourier data we generated. But I think you could smooth it and still get similar results.
Yes, I think so too. Okay.
I think you could.
Yeah. But it's safer to do raw, I guess, especially when you have spikes like in your models, right?
Right. Yeah. If you have like a feature or like a sharp frequency feature like this one.
Yeah, exactly. This would be complicated to smooth out. Yeah.
Right.
Thanks.
Sure.
I have a question on this figure, the F star. What is the value of the F star typically? Because here you normalize the frequency by the F star, but
I guess the short answer is whatever you want it to be. Depends when the feature happens in your model. So
okay. And I have a last question. You said that after 15 days, you were able to detect the signal.
Right. With the kind of like the Radler type signal.
Okay, it's a Radler type signal. That was quite high, in fact. Yes.
Yeah, it was quite loud. Yeah, and especially if you can use the T channel, you can detect it with only a few days. Yeah.
Okay. Stefano?
Yeah, I have a question. Nice talk. Do you expect that if you leave the instrument noise completely free, so let's say 20 PSD values on 20 frequency, still the signature due to the rotation of the instrument would allow you to differentiate a background from that?
So my understanding, and somebody else should chime in if they know better, is that this likelihood isn't valid anymore because AE and T channels now have correlations if the instrument's not stationary or if it's not equal arm. But the T channel should still let you disentangle the signal and the instrument response, I think.
But I think the question of Stefano is more if we have a big uncertainty on the CA, CE, and CT, no?
Mm-hmm. Yes, if we don't know anything about the noise, right?
If you don't know anything, if you know very poor about CA, CE, and CT, how can you deal with that?
Yeah.
Not an easy question. Huh?
Yeah, not an easy question, but it's a key question. So is the sky modulation fingerprint sufficient to extract some information? That's where I have hopes, right?
Yeah. We haven't really looked into that at all. That's a good question. I would expect you could still extract something, but I don't know.
I'm sure Quentin want to, let's say Tyson, then Quentin, and Quentin will continue with his talk that is exactly on the topic.
Thank you anyway.
Oh, good. Yeah, I'll defer to Quentin, but my answer is yes.
Okay.
Your answer is yes. Okay.
I look forward to see it.
Okay. Thank you very much, Robbie. So, and we'll switch to Quentin. Quentin, can you share your slide and start when you are ready? And I'm sure that you're exactly on the topic that we are starting.
Yes. Let's see. Sorry.
We are not slide 1. Okay, perfect.
Okay, you can see the first slide, right?
Yes.
Okay.
Yeah.
So can I start? Yes, I can. So thank
Yes,
you, Antoine.
Thank
you. Thanks to the organizer for allowing me to talk today. So yeah, this is also about gravitational wave background detection, but focusing more on how to do it when you know very little about the noise. And this is a study that has been carried out with Nikos Karnezis, Jean-Baptiste Bail, Marc Besançon, and Henri Michel-Spey. And myself, and this is also related to noise knowledge requirement study that is going on within the LISA science group of the consortium. So I'll start by setting the stage and stating the problem, and I'll spend a little time by listing the assumptions that we've made in this study. And then present to you the flexible modeling of noise that we propose, and then some preliminary results. So, well, as you know, and as Robbie has very well explained, the finding a gravitational wave background of primordial origin is one of the main LISA science objectives, and this is stated in the LISA science requirement documents. Where the 7th science objective states that this is important to understand them for their implications in cosmology and also in particle physics beyond the energies that are achievable by current particle accelerators. Detecting or not detecting actually a primordial stochastic gravitational wave background is important because you can constrain models of the early universe, inflationary models, first order phase transitions, and also explore particle physics beyond the standard model. And so I have stolen this plot from Robert Caldwell, showing you the landscapes, let's say, of the detectors in the context of stochastic gravitational wave background detection. So we see that with vanilla, for example, inflation models, we don't expect to see anything in LISA band except for some particular models of inflation. But yes, things like phase transitions, cosmic strings are maybe more likely to be seen. Yeah, I'll leave these considerations to the cosmologists. And so detecting, there's been quite a lot of literature already about stochastic backgrounds, especially the detection and distinguishing between different types of stochastic backgrounds with parametrized power spectral density models. As Robbie mentioned, there was this software called the SDWG Binner, which is detecting agnostically the gravitational wave backgrounds given PSD, a noise PSD of known shape, or at least parametrized. And it has also been shown by NAM that this analysis can be sensitive to the noise model you're picking. That's why we think one major difficulties is that we have to account very precisely for the model, the noise model that we have to allow for our detection. And we've seen that we cannot rely fully on the physical model of the noise that we have prior to the flight. We've seen that with LISA Pathfinder. Before the flight, the noise model was overestimating the performance, and actually that was good, and we had a better performance, but that shows us that we can not anticipate all the effects of the instruments, and we need to be prepared to that. So we think we need two things. Well, the first is a robust and flexible model for the noise, and second, of course, realistic instrumental data simulations to test the robustness of this model. So this is what our study is about. Of course, we cannot avoid making assumptions, and that's why I will tell you what the assumptions that we have done in this study. So first of all, we're using time-varying unequal arms constellation where the satellites follow Keplerian orbits. So this is okay. We don't think that using more realistic orbits provided by ESA will significantly change the results, but we will test that. Also, we are using an isotropic stochastic gravitational wave background. We are assuming that this is isotropic, and this leads to approximately stationary process. That's related to Stefano's question, actually, but I will talk a little bit more about that. And one crucial assumption is that we assume that the PSD of the noise is smooth on time scale, on frequency scales of the millihertz. And we use time delay interferometry of second generation. We use the pseudo orthogonal variable A, E, and T, and we assume in our analysis that they are orthogonal. This is okay in first approximation. We've also tested this assumption. And we do a strong assumption here also that all the interferometer noises have the same level, which is not what we expect to be in reality. So we'll have to relax this assumption in the future. One thing also is that we're having a template-based search as Rabi, and so this I think is okay if we are doing model comparisons, but of course we can go beyond that, like agnostic searches. And last but not least, we assume that all detectable gravitational wave sources have been removed from the data. So this is a big work before. So just to give examples about these assumptions, here is the stationary assumption. So variations of the power spectral density of the stochastic gravitational wave background as a function of time during 1 year of mission for the TDI variables A and E. So these variations are 1 part to the 1,000. So these are not a lot, and we've not tested that yet, but we don't think we can go beyond the like 10% level for short time scales, so in terms of PSD estimation precision, but maybe that's possible. But anyway, in our study, we assume that the background is stationary. Another example of assumptions test is the orthogonality. So here we have plotted in red the power spectral density of the sensitive TDI variables, A and E, basically. And in black, you have the cross spectral densities of in between all of these variables, A, E, and T. And we see that they are a bit more lower than 1 order of magnitudes with respect to the PSD. So we can say that the orthogonality assumption is okay. Coming back to this modeling that we've come with is so to do robust detection, we use a generic noise model with wide priors, and we want also to inject in our analysis firm knowledge about what we know the best. And what we know the best are the differences between how gravitational waves and noise enter the measurements. So basically the differences in the transfer functions. We may not know in absolute value very well the transfer functions. However, we know them relatively. And so the model that we use is basically the TDI data in the Fourier domain, which is equal to a signal term, which is expressed as a transfer function times the gravitational wave strain. And the transfer function includes the projection onto the arms of LISA and also the TDI response. And regarding the noise part, we have also a transfer function, which is basically the TDI response, although this can change, for certain types of noise. And we have one single link noise vector, which has 6 entries. These are basically the science interferometer measurements. And so if you consider the power spectral density of D, then you can split it in 2 parts, right? The signal part and the noise part, where you have a response functions as a function of frequency that you assume to be known. And you have 2 models, SH for the signal and SN for the noise, which are respectively described by the parameters theta H and theta N. And so here is the modeling of the noise that we adopt. We assume that the log power spectral density of the noise can be expressed as a sum of spline functions. And so this is agnostic, like with respect to any noise model. And the parameters that we estimate are the spline coefficients and the spline knots, or more precisely, the frequency knot locations, and also the frequency knot levels, the amplitudes of the knots. And regarding the power spectral density of the gravitational wave background, this is, yes, a simple power law model that could, yes, represent the effect of cosmic strings, for example, where you have only 2 parameters, the energy density and the power law index. So here are some results that we got. First, on the simulation side, as I said, we're trying to like having at least a different process to generate the data and to analyze them. So here we're generating a stochastic gravitational wave background in the time domain with the software LISA GW response implemented by Jean-Baptiste et al. And we've basically, a few hundreds of independent pixels simulated in the sky, so generated independently, and measured over 1 year observation time. And for the noise, this is less realistic for now. We plan to improve that in the future. We generated from a prescribed power spectral density in the time domain with independent realizations on the 6 links on 6 science interferometer measurements. And then once we have the single link measurements, we apply the time delay interferometry transformation, 2nd generation. And we use the PyTDI software developed by Martin Stab et al. And here is an example of what you get. On the left-hand side, you have the TDI A as a function of frequency. In purple, you have the stochastic background. And in gray, you have the noise. And on the right-hand side, you have the T channel, where, as expected, you see that you have a more attenuation of the gravitational wave signal. Regarding the analysis, we estimate both noise and the stochastic gravitational wave background parameters in the frequency domain, this time with the frequency domain model, using Bayesian analysis, where we sample for the posteriors using parallel tempered Markov chain Monte Carlo. And we use, well, uniform priors for the gravitational wave parameters, but more importantly, we use a kind of a wide prior on the noise PSD. We allow it to vary 1 order of magnitude above or below the physical model that we have, so the true power spectral density. And then we adopt a detection process in a Bayesian way, right? With two hypotheses, hypothesis H0, where you have only noise in the data, and hypothesis H1, where you have noise and signal in the data. And then we compare the evidences using thermodynamical integration and computing the Bayes factor between the two models. Yes, as an example, and this is preliminary, we are able to recover stochastic gravitational wave backgrounds parameters and both the noise parameters in a lot of different configurations of the parameters. And here is an example where, so in black, you have the estimated power spectral density of the single link PSD of the noise, right? Not at the TDI level, but at the single link level. And these red lines that you see are the estimated knot locations with respect to the dashed lines, which represent the knot location that were initially set before running the MCMC. And on the bottom plot, you have some residual plots like of the ratio between the estimated PSD and the true PSD. So I should say that we have also probed the optimal number of knots using transdimensional MCMC. This is Nikos Kanazis that has done this analysis, and we used the optimal number of knots in our analysis. And regarding Bayes factors, we show that we are able, with these assumptions, to detect or not detect a stochastic gravitational wave background with this simple model, depending on their SNR. We have different Bayes factor depending on the strength of the energy density of the of the stochastic background, and we're planning also to probe a wide range of parameter space like the power law index and the energy density. So, as a conclusion, here we are trying to assume no prior knowledge on the noise shape except its smoothness and also its transfer function. And we demonstrated that with some range of assumptions, the detection is possible, but we need to go beyond, right? So we need to use more realistic assumptions. So for example, different noise levels in the interferometers. And as we said before, this will, force us to use models for non-diagonal terms of the covariance matrix, and also include other stochastic processes, as the galaxy is important, and the ultimate goal maybe is trying to do a full agnostic estimation of both signal and noise. This is not like certain to be possible, but we'll see how far we can go in this idea. So thank you for your attention, and if you have questions, I'll be happy to answer.
Thank you, Quentin. We have question. Stas.
Hey, Quentin, very nice. I have first clarification. Can you go a slide up? It's not log B, it's B, right? It's 10 to the 3, it's a B, Bayes factor.
I think it's log.
So B is 10 power 10 to the 3?
Yeah, maybe I got that wrong indeed.
Because that would be huge.
Yes, it's clearly
yes.
evidence.
Yeah, so maybe yes, you're right. This is B. Since I did the extreme evidence for H1 is put at this value in red, so that means that this is B, right? Yes.
Yeah. Okay.
Yeah, sorry about that.
My question is about your conclusion. So you mentioned a few shortcomings in your analysis so far. One is the assumption of the same noise. Another is already forgot. One is that all the other sources are removed and that there are no other stochastic gravitational wave signals. Which one do you think will be the most severe out of these? And maybe one more is a non-orthogonality of A and T. Which one of these could be the most severely affecting your current results? What do you think?
Yes. So let's say we apply this analysis without changing anything and relax the assumptions. I think we will get bad estimates of the variance. I mean the uncertainties if we don't include the off diagonal terms of the covariance. But of course, I think not having a proper removal through the global fit of all the sources is the most crucial thing here, because even though you're probing a wide range of frequency bandwidths, I think this is these kind of analyses are very sensitive. But maybe people have other insights about this.
Thank you.
Stefano?
Sorry, I have 1 million questions. I'll ask one.
Okay,
please.
I mean, how much the orthogonality matters? Because obviously the orthogonality goes through the fact that you assume equal noise on the various detector, right? And
yes, exactly.
The second one is that the transfer function of the noise should play no role, because if you leave the model of the noise completely free and the noise is stationary, you can include the transfer function in the noise model, right? So it must be the time modulation due to the rotation of the constellation plus the orthogonality that allow you to discriminate. What is your sense? What is discriminating between the two?
So, well, you have one main difference, right, between the transfer functions of the noise and the stochastic background is that you have, this projection onto the arms that you can trace back. So there is not only, the TDI transfer function obviously is common, but then you have a different process like, in terms of measurements in the different interferometric channels. So I think that's important to take. To take into account. The other thing about time variations, when you have isotropic stochastic background, then the additions of all the sources in the sky basically make the resulting stochastic process very time independent, but there is some time dependencies that we could exploit, right? This is what I showed here. This is tiny, right? So I don't know if you had this particular kind of effects in mind for discrimination.
I've lost your answer because I have a shaky connection, but what allows to discriminate noise from noise? If the projection effect, if it is not time varying, is just a number.
Well, it's a matrix, right? So, so if it's a matrix, then you have more than one scale factor to use.
I think I'm taking too much time. Thank you.
No, but
it's interesting.
I think we can spend 1 hour on that. Olaf.
Yes, hi. Yeah, thanks for the nice talk. I think the question, you can probably guess what it is because we spoke about it a few times before. Did I understand correctly that you still only assume a single noise parameter for each measurement that you have, so you don't distinguish between different noise sources?
Yeah. This is still correct, and I started analyzing the more realistic simulations with this model, but however, this is still what is assumed in the analysis process, which is as we know not realistic. So we'll see to which extent this this assumption will break, like starting just with having a more realistic simulations that Jean-Baptiste has prepared actually already. So yeah, just need time to do that.
Okay, thanks. I'm curious of the result.
Yeah, yes.
And Robbie, for the last question.
Oh, great talk. Yeah, so I guess I was wondering if you did any comparisons with like a dumber noise model, just with like like a 2-parameter fit, and also like which frame is the stochastic background isotropic in? Is it like aligned with the CMB frame or what?
Yeah, good question. So we don't take into account the dipole, anisotropy due to the reference frame, yes, of our galaxy with respect to the CMB. So this is actually investigated by Henri in Chospé and has been also investigated by other studies, but I don't know. I don't remember them in top of my head, but yes, this is something that Henri is looking at, but this is not in this simulation.
Okay, cool.
Thank you. If there are no more questions or no more million of questions, let's thank you, Quentin, again, and
thank
then
you.
We will switch to Natalia. Natalia, are you ready and ready to share your slide?
Hi. Yes.
Hi, Natalia.
Let me try. Can you see them?
Yes, not yet in the presenter mode, but we see Keynote. Now we have a black screen.
Oh, no.
At least I have a black screen.
Let me do this, and then it probably will work. It's because they switched to another screen.
Yes, it works.
Is it? Okay. Okay, so hello everyone. My name is Natalia Korsakova. I'm a postdoc at APC in Paris, and I'm going to be talking about the fast parameter estimation for massive black hole binaries with normalizing flows. So first, I wanted to give a little bit of the motivation why it is important to do that. So we are going to look at the massive black hole binaries, and probably most of you know that what sort of sources are there and where they are located in our sensitivity band. And the important aspect why we want to do fast parameter estimation for them is that many studies, they predicted there will be electromagnetic counterparts. So some say that there will be electromagnetic counterparts during merger. Some say that there might be even some during the spiral phase. And there are different theories that they might be due to the matter or presence of the magnetic fields. But what is important for us is if we want to do the simultaneous observation of the gravitational waves and the electromagnetic signal, we want to be able to do fast parameter estimation to predict, let's say, a sky localization for the signal. To just give the context is that usually when we do parameter estimation, we always use the bias equation and we estimate our posterior distribution on parameters. And we assume for X, we assume the data model, which is the sum of the waveform and the measurement noise. Now, the problem with this equation is that we cannot have the exact solution for the marginal likelihood. Therefore, we need to find some sort of approximations to that. So one way to do this approximation is to do some sort of sampling technique to do the approximate inference with MCMC or nested sampling. And the problem that can be with this method is that this would require the likelihood evaluation, and that could be rather slow. So the other way is to use some variational inference. In this case, you approximate the posterior distribution with some other tractable distribution. Some people are looking into that, but we are not going to talk about this here. The other way is to do the exact inference, but to simplify the model. And the easiest thing is to do the Gaussian mixture model, for example, but this can be too simple. And the other way is to do the invertible models. And the invertible models is what we are going to talk about today. So just to give a simple example that sort of helps to understand how it works, and actually it works in a very simple way, is that if you have, for example, a random variable and you know it's a cumulative distribution function, then you can sample some random variables uniformly distributed on interval from 0 to 1, and then project it using this cumulative distribution function and get your probability distribution. This is just a sort of simple one-dimensional explanation of how it works. And then you can just, using the change of variable equation for the probability density function, applying the chain rule, come up to the equation that you are going to use to do this invertible transform. So this idea is very simple. And the way how we are going to apply it to the real problem is usually called normalizing flows, because in our case, we sample not from the uniform distribution, but we rather sample from the normal distribution. And why would it be fast is that it would be very fast to sample from the normal distribution. And then we want to somehow find a way how we can project samples from this normal distribution to a more complex distribution. And what we're going to do, we're just going to find this function that would be the bijective transformation that would allow us to do this projection. So how are we going to find this function? We are going to do this using the change of variable equation. So that's a very simple equation, and we just need to put some constraints on this equation. So first, as we already said, the function has to be a bijection. Then this function has to be differentiable, and its inverse also has to be differentiable. And then because you use here the determinant of the Jacobian, this determinant of Jacobian has to be tractably invertible. So if we put these constraints, we can cook up our invertible function and make this transformation possible. The other practical constraint that we have to impose is that the calculation of the Jacobian determinant is actually quite slow. So we need to find a way to speed it up. And so we can make it either small or only diagonal matrix, or one of the ways is to make it a trigonal matrix, because the determinant would be just the product of the elements on the diagonal. So taking all these assumptions into account, we think of how can we construct this transform. So one of the first proposed methods for this model was to use simple affine transformation. Affine transformation is just a location scale transformation when you apply the scale and the shift to your variable, and then the log Jacobian becomes the sum of the log of the scale coefficients. So very simple. And then the other problem that has to be taken into account is that if we want to work with multidimensional spaces, we need to find the way to sort of incorporate the correlation between the different dimensions. And the way it was proposed to be done is with a coupling transform. So in that case, we sort of separate our space into two parts, and we we keep one part fixed, and then we transform the other part using the input from the first part, and we do the same in the backward transformation. So one of the first methods that was proposed to implement the normalizing flows was called real non-volume preserving flow. And so in this method, the coupling transformation is combined with a fine transformation. And basically the transformation can be described by this set of equations. And the important thing is that when you do the transformation back, you just analytically can express this in terms of two functions, which sort of represent your scale and your shift. And now the question is how we can make this expressive and how we can estimate these functions T and S. And these functions we can parameterize by the neural network. We can choose, in principle, any sort of the architecture. And by parameterizing it by neural network, we can make this transformation very expressive because we can have millions of parameters and have very nonlinear functions. So the transforms that we use in the practice, we use the combination of this non-really real MVP, and we use it combined with neural spline flows because neural spline flows have demonstrated themselves in the literature to be one of the most expressive of these flows. So they also have a possibility of using a coupling transform, but in addition to that, instead of using the fine transformation, they use monotonic rational quadratic spline transform. So what they do, they simply take their parameter space, they put several nodes in this parameter space, and then they fit the spline. And when you do the inverse transformation, it is quite easy to invert this spline. Now, when we looked at how we can go from the samples from the normal distribution to our posterior distribution and back, we can ask ourselves a question. So what do we do actually in the case of the gravitational waves? Because we don't have access to the direct samples from the posterior. How can we have access to the information from this samples? So what we do, we say that we know our prior, and then we sample a sample from the prior. But then in addition to that, because we know we assume that we know the sort of the noise of our detector, we can generate the simulated data. And by generating the simulated data, we can say that we have access to the joint sample. And therefore, we can condition our transform on this joint sample. And then we train our network in a way that we go from the prior conditioned on the joint sample to the normal distribution. And when we want to sample and actually get our posterior distribution, we condition our samples from their normal distribution on the real data. And in practice, what we do, we compose a lot of transformations. So we have several types of the transforms, and we repeat them many times because the more sort of you do that, the more expressive your transformations can be. And here is just a sort of a schematic representation that these transformations, actually what they kind of do, they estimate the surface and they kind of start from flat surface, and then they curve the surface, and then they get like that. You get the surface of your posterior distribution. For the optimization, we train it by maximizing the total log likelihood of the data with respect to the parameters of the transform. What this means, what it is equivalent to, is that we minimize the Kullback-Leibler divergence between the normal distribution and the samples that are transformed from the samples that we sample from the prior. And when we transform them to the normal distribution, we just sort of try to make our samples as normal as possible. The other problem that we are facing is that the waveforms, especially for LISA, they're quite long, and we need to find the way how we can compress these waveforms. So to compress these waveforms, we can try to find different bases on which we can project them, in which the data would be more optimally represented. And for that, we use the most sort of simple way how it can be done. We use singular value decomposition, and we decompose the matrix that we construct a matrix of a big sort of array of the waveforms, and then from this matrix we find the preferred directions in this new basis, and then for each new waveform we project this waveform on this new basis, and we just take the few coefficients that are enough for the reconstruction of the waveform. So here are some preliminary results. We are still in the progress of getting the final results. The problem happened to be quite complicated, actually, because the signals for LISA have quite high SNR, and it is not so easy to fit them, but we are almost there. And just some results also on the intrinsic parameters. And here is a plot of here is the PP plot showing that we can fit these parameters quite well. And as a conclusion, just want to make a state that this is an independent method to do the Bayesian parameter estimation, and then it is of course it takes time to train, but it is fast in the execution. So this can be this is much faster than sampling, it just takes several seconds, and therefore it can be super useful to use for the low latency pipeline for LISA. Thank you for your attention. Any questions?
Thank you, Natalia. We have a question from Tyson.
Yeah, so turning, I'm thinking about this in a slightly different direction. So I'm thinking about after you've done the slow sampling and you have a bunch of discrete samples from this complicated distribution, and then we eventually want to make those as useful data products for people. And so coming up with a high fidelity way of turning those discrete samples into a continuous distribution that is easy to package up for end users to take advantage of is, I think, an unsolved problem, and I think a really, really useful one. So can you see how this approach could be used in the other direction? If I handed you samples, how would you then?
Yes, so if I correctly understood your question, you say that you already, if you already have access to the samples from the posterior, right, but they are not, they are with a low fidelity and you don't have so many of them, right? How can you, sort of improve your resolution and produce more samples?
Audio. The question was, let's say we have adequately sampled
So sorry, I can't hear you very well.
Tyson, you had echo, and now you had echo, and you are weak, so it's harder.
Tyson, the answer is yes, you can use this.
Can Tyson repeat, and I can answer this?
I can try to repeat what Tyson said, that's why I'm answering. So basically, imagine you have posterior samples from some distribution and dimensional distribution. And using this tool to convert these discrete samples and some continuous function, which is very fast to evaluate.
Yes. So that what I thought I understood from what Tyson said. Yes, the answer is yes. And the answer is that this is actually easier problem. So because in this case, now you are trying, when you estimate this transform, you are trying to condition it on additional data. But if you already have access to the samples from the posterior, you can estimate the function that would allow you to sample samples from the same posterior. So you would sort of fit the surface to your posterior distribution.
Tyson, are you satisfied?
I hope I answered the correct question.
Or you don't want to speak anymore?
How do you guarantee the transform? To guarantee that so Senvan is asking, how do you guarantee the transform and its inverse are differentiable? Well, the way you guarantee that is that you construct it in a way it is like that. So when you construct your transform, you have to follow these three conditions, and you just construct your functions in the way that you can guarantee that. So Tyson has a follow-up question. Is the product of getting this continuous distribution packageable? Could be distributed as one of the data products as part of the catalog? Yes, we can. It can be distributed as a software, maybe. So, for example, for the production of the spritz data, when we were sampling from Lisa Pathfinder distribution, the parameters of the glitches, we produced a software which can sample you from this distribution and sort of distributed the software. So that can be distributed in the form of software. So when you just tell it produce me 1 million samples, and it will do it.
Okay,
so it will involve pre-trained networks. So you would distribute the software plus the estimated weights of the network.
Okay, so you train the network before.
Yes, so you train the network before, and then you distribute it together with parameters of this network.
Okay, I know that you like self-sharing, but there is a question from Michael.
Natalia, great talk. Just wondering, I know in the ground-based case, they kind of had to do some special setup, I think, to deal with not knowing the noise up front, or like, you know, in terms of training, including information about changing noise. I was just wondering if you have looked at that at all, or thought about that, or anything about the noise in the context of Lisa.
So I haven't done this yet. Here, I just assume simple noise that you just sample from in the usual way from the PSD. But in principle, because you create your training data as one representation of the waveform sampled from the prior, plus the noise, you can also vary your noise in a different way. So you can put a different models for the noise variation, and then you can incorporate this in your training data. So that's possible to do.
Okay, thank you.
Thank you. Any more questions for Natalia? If not, thank you, Natalia, for the nice talk, and thank you all the speakers of this session for this very nice session, I guess. I think we will close the session. I remind you that we will have an LDC workshop at, I think it's 5:45, correct? Natalia, you are the chair of the LDC. So
yeah, in 15 minutes. Yes.
15 minutes.
Today
So,
will be a parameter estimation for galactic binaries and for.
sorry, we lost parameter estimation for galactic binary and
Massive black hole binaries as well.
thank you, Quentin. That's nice. We have all the chairs. Okay. Thank you all for this nice session, and I think we can close the session as there. Yes.
Yes, that's everything. Thank you, Antoine, and all the speakers, and enjoy the workshop. Otherwise, we'll see you again tomorrow. Bye.
Thank you. Bye-bye.
Goodbye all.
Bye. Sorry, my connection dropped.